A very good morning to the esteemed chairperson, delegates, and fellow researcher. My name is Deepika, and I am a UGC Senior Research Fellow at the CSIR Central Institute of Medicinal and Aromatic Plants. Uh, it is an honor to present my work here at the 5th Annual Congress on Plant Science and Biosecurity. Today, I will be presenting my research work entitled Comparative Uptake, Translocation and Accumulation of Chlorpyrifos into Varieties of Withania somnifera under hydroponic conditions. In this presentation, we will explore how a vital medicinal plant, Withania somnifera, interact with the common pesticide Chlorpyrifos, providing insights that are critical for both agricultural safety and biosecurity. Let's start with the subject of my study, pesticide. As defined here, pesticide are substance used to control pests, thereby securing our food production and supply chain. They are an indispensable tool in modern agriculture. However, their benefits come at a significant environment and human health cost. The widespread and sometimes unscientific application of pesticides leads to the contamination of soil, water, air, posing considerable risk to non-target organisms, including humans. This durability, the necessity, and the danger is what drives the need for the deeper understanding and better management studies. Uh, The term pesticide is an umbrella for a wide variety of compounds as illustrated in this classification chart. They can be categorized by their targets such as insecticide, herbicide, nematicides, fungicides, miticides, algicides, and rodenticides, or by their origin, natural versus synthetic. Our research focuses on the synthetic organic pesticides, especially a compound belonging to the organophosphorus class. Organophosphates are known for their high efficiency, but also for their potential toxicity. Uh, The specific organophosphate we investigated is chlorpyrifos. Despite widespread ban in numerous countries, chlorpyrifos remains a significant environment and public health concern. While global usage has decreased due to its ban, its residue persists in the environment, contaminating soil, water, and even food chain. Moreover, it is crucial to acknowledge that chlorpyrifos continues to be used at some ground level in certain regions where it hasn't been completely overlaid or where regulations are less stringent. It is one of the most widely used insecticide in India, accounting for nearly 9.4% of the total insecticide consumption. Its mode of action is the potent inhibition of the enzyme acetylcholinesterase, a critical component of the nervous system in both insect and mammals, which make it potentially toxic to human and other non-target animals. The plant in our study is Withania somnifera. It is a very important plant which was used in traditional medicine, used for the adaptogenic and therapeutic properties. The potential for a widely used pesticide to contaminate such a valuable medicinal plant present a serious health concern. Therefore, our central research questions arises: how can we optimize pest management while minimizing chemical contamination? We believe that understanding the fundamental mechanism of pesticide uptake, translocation, and accumulation in plant is the first step towards achieving this goal. To establish the current relevance of our study, we performed a scientometric analysis. The top graph shows a steady and significant increase in research pesticide and plant over the past few decades, indicating a mature and growing field of interest. where specifically the bottom graph focuses on the Chlorpyrifos and plant, show more recent but clear upward trend to research article. The network diagram further highlights that the key research clusters revolve around concepts like uptake, translocation, and degradation. The very focus of our study, this confirms that our research addresses a timely and important scientific question. Now, let me walk you through our extinct varieties of Withania somnifera, Pochita and Nimitli 118. Uniform plants were then transferred to the hydroponic system for the exposure experiment. This control environment allow us to precisely dose the root and study uptake without the complexities of a soil matrix. We also conducted a root absorption experiment and an inhibitor experiment to examine the uptake pathway. The plant was subjected to three treatments. Uh, Control T1 treatment T1, which is at 1 microgram per gram, and a high dose T2 at 5 microgram per gram. We collected samples at multiple times point up to 96 hours. Finally, the pesticide was extracted from the plant tissue from the Quacher's method and the nutrient solution by liquid extraction, and the concentration of the Chlorpyrifos were quantified using gas chromatography. Moving to our result, we first examined the fate of Chlorpyrifos in the nutrient solution itself. These graph A and B shows the concentration of Chlorpyrifos over 96 hours for the Nimitli and Poshita. As you can see, the concentration of control solution, the blue line, decreased very slowly, likely due to the natural degradation. In contrast, the solution containing plant, which is represented by red and the green line, shows a much faster decline. This strongly suggests that the plants are actively removing Chlorpyrifos from the water. This table below quantifies this. We fitted the data to a first order one phase decay model. The key parameters here is the half-life, where the half-life when the control solution is over 200 hours. It dropped dramatically in the presence of plant down to 5.5 hours. In one of the Poshita treatment, the high R-square value indicate an excellent fit for our model. So if the plants are taking up the pesticide, where it is going? This slide answer this question. The two bar graph A and B shows the concentration of Chlorpyrifos in the shoot and root over times. There are three clear takeaway here. Concentration in both the root and shoot increase with both exposure time and the initial dose. Accumulation of significantly higher in root compared to the shoot across all the treatment. We observed a significant difference between the two varieties, with the Poshita variety accumulating considerably more Chlorpyrifos than the Nimitli 118. The star mark denotes statistical difference. The line graph C and D shows the root and shoot concentration factor, which normalize the tissue concentration to the initial exposure concentration. This further confirms that the root are the primary sink for the Chlorpyrifos uptake and accumulation. Finally, we applied the kinetic model, uptake kinetic model to the root concentration data using a first order one compartment kinetic model. This described in the given equation. This model help us to calculate a rate constant for uptake k root. Uh, the graph shows a very good fit for our experiment data. The points represent the concentration of the chlorpyrifos. Uh, Concentration of the chlorpyrifos. Comparing the varieties, we can see that both low and high concentration, the rate constant for the Poshita is much higher than the Nimitli. This consequently confirms that Poshita root take up chlorpyrifos at a faster rate. Finally, we applied the same kinetic model to the shoot concentration data to understand the rate of translocation from root to shoot. However, we are looking at the rate constant for the shoot accumulation or the translocation rate. Again, the model fit the data well. With high R square value, the table of the rate constant reveal a similar trend to the root. The Pocheta variety constantly shows a higher rate constant for the for the shoot accumulation compared to Nimitli 118. This indicate that not only does Pocheta take up more chlorpyrifos through its root, but it is translocated more efficiently to the shoot. Having established the uptake occur and at what rate, we next investigate how it occurs. This slide explore the potential pathway. The first diagram shows a cross section of a plant root, water and solute on which enter the plant through two main routes. The apoplastic pathway moving between the cell and the symplastic pathway moving through the cell by crossing the plasmodesmata. To enter the xylem for the long distance transport, substances must eventually cross the Casparian strips present in the endodermis. This transport across the cellular membrane, a lipid bilayer shown in the diagram 2, can be either passive without the consumption of energy, or by active. But our result shows that the uptake is totally passive. The graph on in the panel third shows that when the plants are treated with inhibitors like sodium azide, silver nitrate, and which disrupt the energy production and block water channel respectively, the uptake of chlorpyrifos was not reduced by addition of these inhibitors. This shows that chlorpyrifos uptake is a purely passive process but can take help of non-specific lipid transfer protein. Finally, we wanted to explore a potential molecular mechanism for the small amount of chlorpyrifos that is transported within the cell. We investigated its interaction with non-specific lipid transfer protein, or NSLTPs. NSLTPs are the small abundant protein known to bind and transport hydrophobic molecules like xenobiotics, and are also involved in the plant defense response. We hypothesize they might act as a carrier for chlorpyrifos. This slide shows the result of molecular docking simulation, a computational technique to predict how a protein which is red in color and a ligand chlorpyrifos which is in yellow color might bind. The different panels show various binding protein, highlight the specific molecular interaction: hydrogen bond which is in green color, hydrophobic interaction pink, and electrostatic interaction red in color. these simulation predict that chlorpyrifos can indeed bind favorably within the hydrophobic cavity of the non-specific lipid transfer protein from Withania somnifera. While this is a predictive result, it provides a possible molecular hypothesis for how chlorpyrifos might be chapened within the cell's aqueous environment. Differences in the sequence and structures of the non-specific lipid transfer protein between the Poshita and Nimitli 118 variety could potentially explain their differential translocation efficiencies, a possibility that needs further experimental validation. Once chlorpyrifos reaches inside the plant, where does the chlorpyrifos residue accumulated in the plant? This answer can be given by subcellular distribution. To answer this, we fraction the cell component into cell wall, cell organelle, and cell soluble fraction. The two bar graph shows a striking pattern in both the root and shoot of both the varieties. More than 80 to 90% of the chlorpyrifos was accumulated in the cell organelle, and a very small fraction was present in cell wall, and in cell soluble fraction chlorpyrifos was completely absent. As we see that Poshita has more lipid content than Nimitli 118. So the accumulation of chlorpyrifos in Poshita is higher than the Nimitli 118 variety. Our hypothesis is that the cell membrane, which is a vast network of lipid polymers, act as a primary binding site, effectively sequestrating and immobilizing the chlorpyrifos before it can cross the cell membrane in large quantities. This sequestration in the cell wall is a key defense mechanism that limits the pesticide translocation from root to shoot. Now coming to the conclusions of my study, Withania somnifera effectively take up chlorpyrifos from the hydroponic medium. The uptake is a rapid passive process and follow first order kinetics. The root are the primary site of accumulation, with the majority of pesticide being accumulated in the cell organelle, which limits its translocation to the shoot. Most importantly, we find significant varietal difference. The Poshita variety exhibit a significantly higher capacity for uptake, translocation, and accumulation of chlorpyrifos compared to the Nimitli variety. These findings have two major implications. First, from a food safety and biosecurity perspective, the Nimitli 118 variety appears to be safer choice for cultivation in area with potential chlorpyrifos contamination due to its lower accumulation. Second, for a bioremediation perspective, the high accumulating Poshita variety could be explored as a candidate for phytoremediation to help clean up contaminated water or soil. I would like to extend my sincere gratitude to Director of my institute, CSIR CMAP, for providing the necessary facilities and conductive research environment, and of course my supervisor, Dr. Pooja Khare. And thank you all for your time and attention. I would be happy to answer any question you may have. Thank you.